Problem number 2. Show that every positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 for some integer q. Let us take a as the odd positive integer. Now divide a by 6 and q is the quotient and r is the remainder. Now represent this using Euclid's division lemma, that is a equal to 6q plus r, where r is greater than or equal to 0 and r is less than the divisor, that is 6. So r can take the value from 0 to 5. Now let us take r equal to 0 to start with. So then when r equal to 0, a equal to 6q, which I can write as 2 into 3q. So 2 is a factor of 6q. So if 2 is a factor of 6q, then 6q is even. That means any number, if you can divide by 2, then that is an even number. So now let us consider r equal to 1. Then a equal to 6q plus 1. Now this is 6q is even number plus 1. If you add 1 to any even number, then that is odd. R equal to 2, that is a equal to 6q plus 2, so it is even number plus 2. If you add 2 to any even number, that is again even. R equal to 3, a equal to 6q plus 3, so this is even number plus 3. So add 3 to any even number, that is again odd. R equal to 4, so a equal to 6q plus 3, so 6q plus 4, r equal to 4, 6q plus 4, so it is even number plus 4, so that is even. Last one, r is equal to 5, then a equal to 6q plus 5, so even number plus 5, so add 5 to any even number, odd. So these three numbers, that is 6q plus 1, 6q plus 3 and 6q plus 5, all three are odd. Therefore, when a is odd, it is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. Next problem. Use Euclid's division lemma to show that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Now let a be a positive integer and b, let b equal to 3. So now from Euclid's division lemma, we have a equal to bq plus r, or here it is A equal to 3Q plus R. Now R is greater than or equal to 0 and R is less than 3. So value of R is from 0 to 2. 0, 1 and 2. Now let us consider all these three values. So R equal to 0. When R equal to 0, A equal to 3Q. Now square both sides. So A square, because we need the square of the positive integer. Positive integer here is A. A square equal to 3 square, that is 9Q square. You can write this as 3 into 3Q square. Now these 3Q square, because Q is a positive integer, Q square into 3. So 3Q square is also a positive integer. Let us consider as m. So this is of the form 3m. When R equal to 1, then A equal to 3Q plus 1. Now squaring both sides, you get A square equal to 3Q plus 1 whole square. 3Q plus 1 whole square is 9Q square plus 6Q plus 1. A plus B whole square is A square plus B square plus 2AB. So now this one we can represent as, let us take 3 outside. So 3Q square plus 2Q. 3 taken out and plus 1. Now this entire thing 3Q square plus 2Q is also an integer. Let us consider this as m. So this is of the form 3m plus 1. Now going further, when R equal to 2, A equal to 3Q plus 2, therefore A square equal to 3Q plus 2 whole square, that is equal to 3Q square, 9Q square plus 2 into 3Q into 2. So 4, the 2 into 4 into 3, that is 12Q plus 2 square, that is 4. So write this as like this way. This can be written as, this can be written as 9Q square plus 12Q. Let us split 4 as 3 plus 1. So now taking 3 out from the first 3 terms. So this is 3Q square plus 4Q plus 1. So now 3Q square plus 4Q plus 1 is also an integer. Let that be m. So it is 3m plus 1. Hence, square of any integer, a is an integer, square of any integer is of the form either 3m or 3m plus 1. I can explain this one a little better because some of the students may not be able to understand what does this mean. Now let us take A as 1. A equal to 1. Then A square also 1. So this can be represented as 3 into 0 plus 1. So this can be, m is 0 here. So it is 3 into m plus 1 form. Let us take A equal to 2. When A equal to 2, A square is equal to 4. So this can be represented as 3 into 1 plus 1. So that is here m equal to 1. So it is 3m plus 1 format. Now a equal to 3. So a square equal to 9. So this can be represented as 3 into 3. So plus 1 plus nothing. So this is m is 3. So this is 3m. Continuing further, a equal to 4. A square equal to 16. Now you can split this as 3 into 5 plus 1. Now m equal to 5 here, so it is 3m plus 1. Like this, if you continue, the squares of these numbers can be represented as either 3m plus 1 or 3m. Next problem. Using Euclid's division lemma, show that the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. Now here let a be the positive integer and let us divide by 3. Now here divide by 3, then you get q as the quotient and r as the remainder. Now representing in Euclid's division lemma, a equal to bq plus r, or this is a equal to 3q plus r. So now r is greater than or equal to 0 and r is less than 3 because 3 is the divisor. So r values are 0, 1, 2. Now first let us take here r equal to 0. When r equal to 0, a equal to 3 cube. So now taking the cube on both sides, so a cube is equal to 27 cube. Now this can be written as 9 into 3 cube. So 3 cube is an integer. Let us take it as m. So this is of the form 9m. Now when r equal to 1, then a equal to 3q plus 1. Taking the cube on both sides, a cube equal to 3q plus 1 whole cube. Now this is, now you know a plus b whole cube, that is a cube plus 3a square b plus 3ab square plus b cube. So now here 3q whole cube, that is 27 cube plus 3a square b, 3 into 3q square, so 9q square, 27q square, 3ab square, 3 into 3, so this is 9q plus 1. Now here also let us take 9 out. If you take 9 out, this becomes 3 cube plus 3 square, 3 cube plus 3 square, then 9 if you take out, it is only q plus 1. Now this entire thing is an integer, so let us represent as 9m plus 1. Now when r equal to 2, a equal to 3q plus 2 whole cube. Now this is 3 cube, 27 cube plus 54 q square, 54 q square plus this 1 4 9 36 q plus 2q, that is 8. Now here also taking 9 out, so 3q plus 54 divided by 9, 6q square plus 4q plus 8. This entire thing is an integer, so take it as 9m plus 8. So cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. Just like we have shown in the earlier case, here also we can explain what does it mean. Now first let us take a equal to 1. When a equal to 1, sorry, a equal to 1. When a equal to 1, a cube also is 1. So now you can consider this one as 9 into 0 plus 1. So this is 9 into m plus 1, where m equal to 0. Now a equal to 2. When a equal to 2, so a cube equal to 8. So this is 9 into 0 plus 8. So this is 9m plus 8. Here also m equal to 0. Now a equal to 3. So it is a cube is equal to 27. So 27 is 9 into 3 plus 0. So this is 9m. So where m equal to 3. So let us take one more. A equal to 4. So a cube equal to 64. Now 64 can be represented as 9 into 7, that is 63, plus 1. So this is 9m plus 1, where m equal to 7. So the cube of any positive integer can be represented in one of these three forms, that is 9m or 9m plus 1 or 9m plus 8. Last problem. Find the maximum number of students among whom 1001 pens, so pens 1001, and pencils 910 can be distributed such that each student gets same number of pens and same number of pencil. Now you have to find the maximum number of students among whom you can distribute these pens. But if one person gets say 15 pens, everybody has to get 15 pens. If one person gets, suppose say 13 pens, every person has to get 13 pencils, every person has to get 13 pencils. So it doesn't mean that everybody has get to, if one person gets 10 pen, he has to get a 10 pencil also. No, if one person in the group gets x pens, everybody has to get x. If one person in the group gets here x, here y pencils, everybody has to get y pencils. That is what it means. So here what we need to do is we need to find out the HCF of these two numbers. So the HCF of these two numbers is the maximum number of students among whom we can distribute these pens and pencils so that each one gets the same number of pens and same number of pencils. So let us use Euclid's division algorithm to find out the HCF. In this case, A equal to 1001, B is 910. So now you have to write A equal to BQ plus R. A equal to 1001 equal to B is 910. Of course, it will go only once here. So let us find out the remainder R here. So 1001 minus 910. So this gives 91. So remainder is 91. So remainder is not 0. So 910 is not the HCF. So now let us go to the next step. So 910 equal to, so here this will come here 91. So how many times will go in 910? 10 times. So remainder here will be 0. So now the remainder is 0, then the divisor is the HCF. This is the HCF. So it can be now 1000 pens and 900 pencils can be distributed among 91 students so that each one gets the same number of pens and same number of pencils. So each person, that all the 91 students, will get 11 pens and 10 pencils.